Hello and welcome. I am Bernd Fischer from the University of Stellenbosch in South Africa. I will present our experience in using grammar-based testing for student compilers. This is joint work with my students Phillip van Heerden and Moeketsi Raselimo and with Kostas Sagonas from Uppsala University in Sweden. Our starting point is that we don't like to write compiler tests by hand. So the obvious question is, can we automatically generate from a context-free grammar test suites that are as good as manual ones? By good enough, we mean that the generated test suite reveals as many faults and crashes as a manual one and covers as much of the system to be tested. But especially for teaching, we also want precise oracles, both syntactically and semantically. We want to know whether the compiler should parse the test or should throw a syntax error. If it parses the test, we want to know whether it should throw a specific semantic error or compile cleanly. Here we provide an answer for the question above for a little language. In particular, we look at AMPL, a modest programming language that has been used at a second-year computer architecture course at Stellenbosch. On the left, we see the complete context-free grammar for AMPL. It is indeed a quite modest imperative programming language with the usual constructs. On the right, we see the list of errors that the compilers can raise. Again, this is pretty much what we would expect. Several classes of syntax errors, some scoping errors, and a bunch of type errors. The task the students were given was to write in C a single-pass recursive descent compiler from AMPL to the Jasmine Java bytecode interpreter. They were given about 60 pages of documentation, which included the CFG and the list of error messages with informal descriptions when they needed to be triggered. For our experimental evaluation, we used the 61 final submissions that built cleanly and passed some basic smoke tests. Think compiling Hello World. We also took the test suite that the instructor used for marking the submissions. We first focused on syntactic test suites, where we only have a syntactic oracle. That is, we only know whether the test case should be parsed or contains a syntax error. Because this oracle is relatively weak, syntactic test suites are typically used in crash testing, not functional testing. The oracle itself is typically built into the test suite construction algorithm. We know whether the test produced by a given algorithm contains syntax errors or not. These algorithms are typically derivation-based. They apply the rules of the grammar in some specific fashion. For the construction of positive test suites, we used a generic cover algorithm, which is shown on the right, together with a variety of different coverage criteria. These are pretty much standard, like rule coverage or context-dependent rule coverage. We also used simple random derivations. For tests with guaranteed syntax errors, we used our work on rule mutation from last year. Let me now show you some experimental results. First, we look at the longer and longer derivations produced by the sequence of coverage criteria shown below. There is a claim in the literature that such better coverage of the input structure also leads to better system coverage. This is indeed also the case here, as the box plots on the right show. On the x-axis, we have the different criteria. On the y-axis, we have the statement coverage for the tested compilers. The orange line denotes the median, the boxes denote the interquartile ranges, and the whiskers indicate 95 and 5%. Outliers outside that range are shown as circles. We see that the coverage inches up when we go from symbol to four-step derivation coverage, but the improvements are relatively small, from 60% to about 66%. And we are topping out at 67%, even with the best criteria. All of this falls far short of the 75% that the positive test cases from the instructor give us. The results are even worse if we look at error detection. Even in the best case, we detect parsing problems, that is, compilers rejecting a valid program, only in 20 submissions, while the instructor's test suite does this for 50 submissions. The difference is somewhat smaller if we look at crashes triggered, but overall, these test suites are not very good in spotting errors in student code, which should be easy, right? Next, we look at random derivations. Note that there is a huge risk to introduce bias into the constructed test suites. Just to give you an idea, we report the results using a K-level rule-weighted breadth-first expansion with minimum yield completion with random tokens, duplicate preservation, and fixed overall test suite token budget to create tests. But if you change any aspect, the results can change. With that said, we see that very small random test suites are worse than systematic, but as they get bigger, they get better and outperform the systematic test suites. That holds both for coverage seen above and for error detection. In fact, for very large test suites, about 6,000 tests with a total length of 500,000 tokens, we achieve almost the same coverage as the manual test suite, and although we still uncover fewer parsing errors, we trigger slightly more crashes. Even better, if we combine a large random test suite with positive and negative systematic test suites, then we do perform pretty much on par with the full manual test suite. Code coverage is slightly lower, error detection is slightly better, and we find an error in every single student compiler. So, going back to our original question, we can indeed generate comparable test suites at least for little languages and at least for crash testing purposes. The question now is, how do we go beyond crash testing? And the answer is obviously, we need semantic test suites with precise semantic oracles. We say an oracle is semantic if it tells us whether a test case satisfies all given contextual constraints or fails with the expected error message. Here we consider only scoping and typing rules as contextual constraints. We use a property-based generate and test style algorithm to produce semantic test suites. We start by adding semantic markup to the rules, that is, tokens that encode the contextual constraints. Here is an example. On the left, we have the original grammar rule for a variable declaration. We know that the IDs are declared here and need to be added to the symbol table. We can encode this knowledge with a decal markup on the ID tokens shown on the right. We then random generate test skeletons from these rules as before. These skeletons contain markup tokens, so they are not valid tests yet, but we post-process them in a single rendering pass. In this case, rendering tries to pick identifiers so that the test satisfies the scope rules. In the first example, it picks 3 different names, x1, x2, and x3 for the ID tokens, and inserts x2 and x3 into the symbol table. Note that the program name x1 is not inserted. This is part of the language specification. Skeletons that cannot be rendered are thrown away. In the second example, rendering the ID ref markup token triggers a name lookup in the symbol table, but since x1 is not inserted, the lookup fails. This means that the rendering engine must maintain a small symbol table to interpret the markup tokens. Let's look at the encoding of ample scope rules in some more detail. We need to add some lightweight markup to a few rules only. This is the entire set of modified rules. We only need a few different types of markup tokens. Decal and ref as before, enter and leave to manage scopes, and something for initialization and cleanup. Note that decal always inserts into the current scope, but the context-free structure of the skeleton guarantees that the scopes are well formed and that decal always works on the correct scope. The last thing we need to do is to fix how the markup tokens are interpreted. We use functionality from the rendering engine, but we don't hardcode this. Instead, we specify explicit mediator mappings. For example, we specify that decal calls the declare method of the scoping model with the unit namespace u as argument. All callbacks return a string that is then printed. For decal and ref, this is the name of the ID. For everything else, this is simply an empty string. The explicit mediator specification is very flexible, and we can also use it to break the contextual rules. That is, we can inject specific errors into the generated tests by overwriting some mediator mappings. For example, we can create tests that should trigger the error multiple definition of identifier if we change the handling of decal to return a name that is already in scope instead of a fresh name. So let's look at an example. Here is a skeleton with two declarations. And if we overwrite the mapping for decal to use the lookup method, then rendering produces the repeat declaration for X. Actually, this works only because the overwriting wraps the mediator into try-catch block and falls back on the default. In this way, the first call to decal first fails on lookup because the table is still empty, and then defaults back to the original insert, which adds X. The second call then succeeds with this X on the lookup. Similarly, if we want to test for the error class unknown identifier, we change the mediator to return a fresh name that is guaranteed not to be in the current scope. We have used the same mechanism to encode typing rules as well. This is of course a bit more involved, so let me give you just the basic ideas here. First, we add type annotations as markup tokens to the rules. For example, the expression used in a while loop must be a Boolean, so we add the : bool type annotation to expr. The annotations on the rule head are preconditions. For example, the rule factor goes to not factor can only be used in a structural context where a Boolean value is required, like in the while loop. The annotations are translated into operations on a type stack where preconditions become pushes and everything else becomes pops. The rendering engine then interprets the stack operations. When it sees a push, it simply pushes the value onto the stack. When it sees a pop, it checks that the top of stack has the expected value. If so, it pops, otherwise it discards the skeleton because it cannot be type correct. Finally, we need to integrate the symbol table into the typing rules as well. We do this via mediator mappings that can access the stack. For example, if we have an ID token at a reference position, like in an expression, then lookup checks the expected type on the stack and searches for a visible name that has been declared with this type. There are a few more tricky aspects to this, like type correct assignments or function calls, but read the paper for this. Let me show you two interesting examples of errors that we have found in the instructor's own compiler by using this mechanism. Here is an example where the compiler accepts the input, but should find the injected semantic error. The assignment let b1a equals O is incorrect because O is a function, not a variable, but the compiler cleanly generates code. In the second example, the instructor's compiler throws a spurious error message about incompatible types. But the actual parameter GS81 does have the required type integer array. There are more details and more examples in the paper, so read up if you're interested. Finally, to conclude, we experimentally evaluated existing grammar-based test suite construction methods for testing student compilers. We found that test suites based on systematic coverage criteria cover less code and find fewer errors than the instructor's manually constructed test suite. We also found that random test suites are better than systematic test suites of the same size, and that a combination of both outperforms the manual test suite for crash testing. We then introduced a lightweight extension to guarantee semantic properties, which is based on markup tokens that are added to the rules and interpreted during the test case rendering step. The evaluation of this was promising, and we found several errors in the instructor's compiler implementation and in all student compilers. For future work, we will first look into a test case reduction method. We also try to apply our approach to more complex languages, perhaps something like Rust. Thank you.